guys, so welcome back to Trace Over Time. So we're going to continue our lecture on open quantum systems from where we left. So we were learning about the postulates of quantum mechanics last time. So let's make a quick review of what we learned in the first lecture on open quantum systems. So the first postulate was, where does my state exist? Where does my quantum state exist? The answer is Hilbert spaces. Okay, as simple as that. Now, and then the second postulate was asking about how do I combine my two Hilbert spaces? How do I combine my two quantum systems to make one quantum system, right? So, what's the answer? We make use of this operator, or really like an operation called the tensor product, and we also learned how to do the tensor product between two vectors, two operators belonging to two different Hilbert spaces. And then we learned about the third postulate. The third postulate was asking about how does my state evolve with time. Okay, so today we're going to learn a little bit more about the third postulate, about the evolution of time, and then we're going to continue learning about the other postulate, that is the fourth postulate, known as the asking the question about how to make measurements of a quantum system. Okay, still now we have been dealing with closed quantum systems only, and for this lecture also we'll be dealing mostly with closed quantum systems, but we're going to learn some interesting things that you might have missed in your earlier courses. Okay, so the third postulate was about time evolution, and we learned about if I have a certain vector at psi 0, then we know that psi t is given by the unitary transformation from t equals 0 to t equals t, right? So this is one way. This is one way to talk about how a state evolves with time, with an unitary operator, also known as the time evolution operator. And another way to deal with time evolution, we saw that it could come from here also. We know it already. It was the Schrodinger equation, basically. So what was the Schrodinger equation? Schrodinger equation is just this thing. We're going to take h cross equal to 1 everywhere. Okay, let's make this clear from now on. Okay, so that's what we learned. That's the last thing we learned when we were learning about the third postulate. Okay, so we learned that if the Hamiltonian is time independent, then we use this unitary operator, which is the Dyson time ordering, t plus of e to the power minus h t prime dt prime, and t prime goes from 0 to, let's say, t, whatever time we're gonna take the evolution to. Okay, so that's what we learned. If the Hamiltonian is time dependent, and this is for when the Hamiltonian is time independent. And let me write that one also. This was for time independent. Okay, so that's what we learned. So let's connect these two. Let's connect these two things using a certain. You can just take a derivative of this and come to here, but we're going to learn about something interesting today, known as the spectral decomposition of a Hermitian operator, or for any normal operator. I'm going to talk about these things. I'm going to explain to you what a normal operator is, what a Hermitian, what Hermitian operator is, but what the spectral decomposition is. So basically, it's just representation of a certain operator as a sum of its eigenvalues and the projection operators corresponding to those eigenvalues. Okay, so I'll explain it to you in a moment. So the spectral theorem is that we have a certain linear operator A that is defined in a vector space V, and it takes it from V to V. And for this operator A, it obeys a certain relation called A dagger. A is A equal to A dagger. only if and only if and only if A can be written as a summation of A, let's say small a lambda a. Okay, where these A's are orthonormal basis vectors for B. So which are also the eigenvectors of A with respect to the eigenvalues lambda A. Okay, so let's say that again. The spectral theorem says that if I have an operator A acting on the vector space B and maps to the vector space B again, so this relation is satisfied if and only if A can be represented as this summation where lambda A, this A's are the orthonormal basis vectors for B. Okay, and these A's are also the eigenvectors of A with respect to the eigenvalues lambda A. So this is our spectral theorem. Okay, so if it's a normal operator, we can always express it this way, and also vice versa. If we can express it this way, then it's a normal operator. Okay, so this is a spectral theorem. So let's see what other operators that we know are normal operators. Okay, so what do we know about the Hermitian operators? Hermitian operators are defined as we know that for Hermitian operators A dagger equals to A, and for unitary operators, let's say A dagger A equals A dagger equals to I. So that's for unitary operators, and this is for Hermitian operators. So let's check for Hermitian operators first. So if A daggers is equal to A, right? So then you can just put A here, and then you can put A here. So it means that A square is A square, right? So it is a normal operator. So no matter what order you put the A dagger in, it will always be equal, right? So that's why Hermitian is a normal operator, Hermitian operators, and the unitary operators are that's just right there in the definition that they are normal operators. But the extra condition for unitary operators is this this A dagger A, this product has to be equal to identity. Okay, so let's check about the how the what we can say about the Hermitian operators and the unitary operators based on this theorem. We can make a little bit of analysis. So for Hermitian operators, we know that, let's write Hermitian. We know that A dagger is equal to A. Okay. So let's do the spectral decomposition theorem on it. Okay. So if I can write A as summation lambda AA, then A dagger would be obviously A lambda A star AA. So let's put this here, right? So it would mean that summation A lambda A star AA is equal to summation A lambda A. So we can see that term by term, these AA's are the same. So what would that mean? That would mean that would imply that lambda A star equals lambda A. So what satisfies, what kind of quantity, what kind of complex number satisfies this? Exactly, real numbers. So what kind of numbers? What kind of numbers? Actually, real numbers are a subset of complex numbers. So you can call real numbers as complex numbers. It's no big deal. But this tells me that lambda A is real. Okay, which we already knew about Hermitian operators, which is why we take when we when we say talk about observables, we talk about Hermitian operators. That's why we do this. Okay, so that the outcomes of our experiments are real numbers. Okay, so for unitary operators, let's see what we get from the spectral decomposition theorem. Let's see what we get. So we know that in unitary operators, I equals a dagger a. That's the definition of unitary operators. So let's just put these things here. Okay, in place of a dagger and a. So what we get here, we will get this summation a lambda a star a times, let's use another index here, a prime lambda a prime a prime a prime. And what would this give me? This would give me a certain summation with a and a prime. So we can combine these summations. This is actually another interesting thing about quantum mechanics, that we can just exchange these summations. This is not always possible. This thing is not always possible if the summations don't converge. Even if there are infinite sums in quantum mechanics, we know that they converge always. So in this case, we can exchange the order of our summations. Okay, so this will be lambda a star, lambda a, and then a this thing, whatever, and then a prime, right? So this is a known thing that we know, that is the delta function a comma a prime, which is equal to 0 if a and a prime are not the same. So this only selects the values of the summation for which a is equal to a prime. So we can just write it as summation a. Let's say that a prime is equal to a, then this, what will this become? This will become lambda a mod square, and this will become just 1, and then a. Okay, but now let's erase this one, since we've already, I assume that you already understood, and this is nothing that I need to refer to later. So let's do this thing, this identity operator. So this is the right hand side of our equation. Let's deal with the left hand side now. So identity operator from quantum mechanics, we know about the completeness theorem, right? If this is a complete basis, then the identity operator will give me, I can write it in this form: summation a. Okay, this is if my space is if my Hilbert space is completeness theorem. So what does that mean? So this thing, since I is equal to a dagger a, so this thing will be, oh sorry, this thing will be equal to this thing. Okay, so then it means that a equal to summation a lambda a mod square a. Again, if we see term by term, it would mean that lambda a square equal to 1 for all a. Okay, so what does that mean? So this thing has no, this thing is just this thing has no magnitude. It is unitary. This thing is how do you say it? In a complex, if a complex number has an absolute value of 1, it means that it's just a unit vector with certain phase. So that's the case of lambda a here. So that's the case of the eigenvalues of a unitary operator. Okay, so this means that, so lambda a is just basically a phase, right? Theta a, where this theta a is just a real number. So these are just phases. These are the eigenvalues of a unitary operator. These are just phases. Okay. So that's what we get applying the spectral decomposition theorem to Hermitian operators and then unitary operators. So let's erase. Now we can do one thing. We can define some functions of normal operators. Okay. So if we have a function that takes a complex number and gives me a complex number, let's say we have a function defined in C, mapping to C. We can extend it to the case of normal operators by defining FA as where A is a normal operator. Using the spectral decomposition theorem, we can just define this A. Okay. So you can notice that this function operates only on the eigenvalues. Okay. Now let's prove the equivalence of the two evolution laws. Let's write it somewhere. It's in a different color. Do I have different colors? Yeah. Let's write it up here. Okay. So our first one was psi t is operator. These jokes are terrible. Okay. T 0 to psi 0 where psi ut is equal to e to the power minus iht. Let's just write that one. We don't need this variable form. So e to the power minus iht, and the other one was the Schrodinger equation. Okay. That was minus ih psi t. Okay. So one way to talk about the equivalence of these two theorems is through, we can just take the derivative of this thing. So just ddt of psi t is the same as ddt of the first equation in there, to the power minus iht psi 0. Okay. So we can just operate it like this and bring out the h, which is bring out this quantity. This is not trivial though. This is, I mean, you have to think about it, why this is possible. Usually we take we take a derivative of a certain operator, and we take a derivative of a certain function, exponential function, and we just take the constants out. But now here we have an operator, but we're still being able to take it out. So it's not trivial. You should try to prove it yourself. Let's just, I will give you the recipe to prove it. Let's just take an operator A and take an exponential of it and then take the derivative. But for this thing, first of all, express e to the power at in terms of its Taylor expansion. So that would be like I plus A by 1 factorial plus A square by 2 factorial plus so on. So using this, you can get that you will get A to the power at. Okay, try to prove it. So I can just take this thing out, which is like h to the power minus iht psi 0, just minus ih ut psi 0, and that is just minus ih of psi t. Okay. So using this one, we proved this one. But there's another way to do it, which is more, which will give you a little bit of practice about the spectral decomposition theorem, and give you a little more insight about what's going on exactly. Okay, so there's another process to to bring out the equivalence between these two equations. Okay, so let's go. So what we are going to do here is we start with the spectral decomposition of the Hamiltonian H. Okay, we have this Hamiltonian from here. We can write it as lambda A. Okay, so what does it mean? It means that the unitary operator ut, which is equals to e to the power minus iht. Okay, so you can write ut as e to the power. This is again the spectral decomposition theorem, minus I lambda at a. Okay, just write h in this form, put it here, and you will realize that ut is actually e to the minus I lambda at and times this thing. Again, you need to do something like a little bit of calculation to realize if you don't see it exactly. Okay, now what we do is since the eigenvectors of H are a basis, again from the spectral decomposition theorem, we decompose the psi t in the basis. Okay, we decompose psi t in this basis and write psi t as summation a certain psi a t times a. So what we have done is we have taken the psi t and we have expressed it in the same basis as the Hamiltonian. Okay, and now what we're going to do is we're going to take the derivative of this thing. So ddt psi t is equal to summation a ddt psi a t times a. Okay, so that's what we did, and then we have this this thing. Okay, now we're going to take the right hand side of this. So here we have dealt with the left hand side of the Schrodinger equation. Now we're going to deal with the right hand side. Let's erase it. So minus IH psi t is equal to, if we do the spectral decomposition, it will become A lambda A of psi t. Okay. Now we did all this. We did this thing. If you see that we took the psi t and expressed it in the basis of the Hamiltonian. Okay. So we're gonna we're gonna put this here. So we need another index. So that would be minus I a prime and this lambda a and then psi a prime. So we're putting this here. So psi a, it has another index, psi a prime of t and a times this thing and then this part a prime. So again we can see that this is our delta function. This is our well-known delta function. Okay. So what this means is a is going to be equal to a prime. So what this will give me that we're just going to put a equals a prime. Again, the summation will select the terms where a is equal to a prime. Okay. So this will be minus a minus I summation a lambda a psi a t A. Okay. Now what we're going to do is, should I erase this one? Yeah, let's erase it. But let's keep this part. Okay, so for this thing, so for the Schrodinger equation to hold, we need that this thing is these terms. So in the summation, inside the summation A, these terms to be equal to these terms. Again, inside the summation A, we need the equality term by term. Since we have summation A and summation A here, so that the term by there should be an equality term by term. Okay, so that would mean that d psi A dt for this part, for the left hand side part, which is this one, without the summation symbol, d psi A dt should be equal to minus I lambda A psi A t, which would imply to me that psi A t is exponential e to the power minus I lambda A and psi A t. No, I'm sorry. I'm sorry. Psi A is not in this thing. So it would give me that minus I lambda A is psi A of 0. Okay. Because we're going to integrate it from time 0 to time t. So we're going to get this one. Psi A t, the evolution of psi A is psi A with respect to time is depends like this on psi 0. Okay. So now we're gonna put this in our psi t, in our summation. So psi t would be to summation A e to the power minus I lambda A t psi A 0 A. Okay. Now we're gonna do a certain very interesting thing. Okay. We're gonna divide this summation into, we're gonna, like we did in the earlier calculations, whenever we found the delta function, we just took one of the indices. Now we're gonna introduce another delta function inside. We're gonna turn one summation into two summations. So it's just it's a neat mathematical trick. Okay, so this will be e to the power minus I lambda A t A, right, into times A prime psi A prime of 0 A prime. That's it. So what we did is we introduced a delta A prime here. Sorry, A comma A prime here, and we divided this summation into two parts. Okay, the summation A, summation prime. We took these things, this part and this part, into one summation, that is A, and then we took psi A, and then we wrote the delta function as A prime. So then here will be one A, there is another A here, so we get two A's, and we know that about the completeness and stuff. Okay, so anyways, so that's what we do in this. And then what does that tell me? We know that about divided the sum into two parts. Okay, two parts, A and A prime, and we introduced the delta function so that we could do it. And why did we do it? So delta function, I can write as A and A prime are there, and then I introduce it here, and then I divide this product into two products. So I get this one, I take this part and the A here, and then I get another A here. So this becomes a part of the summation A, and the rest of the part is taking this one and the a prime here. So this is the other summation. So when we look at this, what was it exactly? It was the spectral decomposition of, I'll tell you. So if you remember, I don't know if you remember or not, we did the spectral decomposition of UT. Is it written anywhere? No. So UT, that was equals to e to the power minus IHT. With the spectral decomposition, it was A e to the power minus I lambda A T A A. And that, what was that one? This part. That was just a representation of psi 0 at in the basis of our Hamiltonian, right? So this is this thing, and summation a prime or a or whatever psi a prime 0 a, that is just psi 0. Okay, so this gives me is the same as e to the power minus IHT psi 0, which is ut of psi 0. Okay, so what did we do? We used the spectral decomposition theorem to connect these two formulas. Okay, we took the left hand side of this equation and did the spectral decomposition on it. We took the right hand side of this equation and we took the spectral decomposition on it, and then we got from here to here. So that's what we did using this thing, the spectral theorem. Okay, so that concludes our part about the time evolution. Okay, so in the next lecture we will talk about the next postulate, which is the about measurements of quantum systems. Okay, so tune in. Thank you for watching.